Good morning, good evening, and good afternoon to all. I am Sohan Maity from EC, and today I am going to discuss about the topic properties of electromagnetism used in nuclear magnetic resonance. So today I'm going to talk about the contents which you can see is presented on the screen. The basic topic is about NMR spectroscopy, in which we are going to stress upon different aspects of electromagnetism used in NMR and some basic applications of NMR. What is NMR? Nuclear magnetic resonance. It is a technique used to probe the magnetic properties of atomic nuclei. NMR exploits the magnetic properties of nuclei with non-zero spin, which has an example of hydrogen in MRI. What are the main applications of NMR? Magnetic resonance imaging exploits hydrogen atoms response in biological tissues. It is used in medical science, and the second application on which we are going to stress on today's topic is NMR spectroscopy. It identifies chemical compounds based on the electromagnetic environment around the nuclei. So now the basic needs of NMR. For that, we need to know about some introduction to electromagnetism, where we need to know what is electromagnetism. It is one of the four fundamental forces responsible for the interaction between electricity and charged particles. And secondly, we need to know the basic things about Maxwell's equations and how electric and magnetic fields interact and propagate. So the key concepts are electric field caused by the stationary charges and magnetic field produced by moving charges or currents. Introduction to electromagnetism. So now we are going to look into the Maxwell's equations. These are the basic four principles of Maxwell's equations: the Gauss's law for electric fields, the Gauss law for magnetism, the Faraday's law of induction, and the Ampere's circuital law. You can see these are the four fundamental equations required in Maxwell's equation to know the basic things about NMR spectroscopy. And this is the particular image in which we can see how Faraday's law works. So now we are going to look into an animated video about what is NMR. It is a nuclear magnetic resonance is a technique that uses magnetic fields and electromagnetic frequencies to study molecular structures. For high magnetic field, superconducting magnets are used. Lower fields can be generated by permanent or electromagnets. Samples are inserted in the center of the magnets and positioned in the NMR probe. So the sample is located at the position of the strongest field and highest homogeneity of the magnet. The NMR probe consists of coils that are used to excite the sample and record signals response at radio frequency. The basis of NMR is that nuclei behave like microscopic magnets in the magnetic fields. The spin around the main magnetic field just like a spinning top. This motion is called precession. See, here the spinning top is spinning, which the motion is called precession. The frequency of precession is proportional to magnetic field strength. Additional local fields are introduced by changing electron densities in a molecule. The higher electron density results in more shielding, then a lower local field and lower spinning frequency, which results in less shielding. Now we are going to learn about spin and magnetic moment of nuclei. So what is nuclear spin? Nuclei with odd number of protons and neutrons exhibit an intrinsic angular momentum called spin. The associate magnetic moment mu is given by mu equals to gamma I, where gamma is gyromagnetic ratio and I is nuclear spin with angular momentum. Interaction with external magnetic fields. When it is placed in a magnetic field, nuclear magnetic moments align parallel or antiparallel to the field, corresponding to different energy levels. Now we are going to study about Zeeman effect and energy splitting. What is Zeeman effect? In the presence of static magnetic field B naught, the energy levels of nuclear spins split. The difference between the energy level is delta E equals to h cut gamma B naught. Here, gamma is gyromagnetic ratio, B naught is the strength of external magnetic field, and h cut is reduced Planck's constant. Now we are going to see about energy transition. The nucleus can transition between these energy levels when exposed to an electromagnetic wave of matching frequency. Now we are going to study about Larmor frequency. It is the most important part of NMR spectroscopy. Larmor precision. In a magnetic field B naught, nuclear spins possess around the direction of the field at characteristic frequency called Larmor frequency, which states that omega naught equals to gamma B naught, where gamma is gyromagnetic ratio, omega naught is angular frequency, and B naught is magnetic field strength. And the resonance condition for this is frequency mu of the applied radio frequency RF field must match the Larmor frequency, where mu equals to gamma B naught by 2 pi. Now we are going to look at a video explanation. In NMR, the frequency of the excited nuclear spins can be measured from the electric currents they induce in the coil. Fourier transformation of the time domain signals result in frequency spectrum with a signal for each different nucleus. The different frequencies recall chemical shifts as they depend on chemical structures of the nuclei. In practice, spectra are measured for all hydrogen nuclei at once, which results in the ethanol spectrum with different peaks at different chemical shifts. Now we are going to study about relaxation in mechanism in NMR. It has T1 spin lattice relaxation, which describes how it follows exponential recovery, where mzt equals to m naught 1 minus e ki power minus t by t1. where mz is the longitudinal magnetization at time t, m0 is equilibrium magnetization, and t1 is spin lattice relaxation time. Similarly, the t2 spin-spin relaxation, where describes dephasing of spins due to interactions between them, leading to decay in the transverse magnetization, where mxy of t equals to mxy of 0 e to the power minus t by t2, where mxyt is the transverse magnetization and t2 is the spin-spin relaxation time. Now we are going to discuss about electromagnetic shielding and chemical shift. Electromagnetic shielding. As we have seen in the video, in molecules, electrons generate small local magnetic fields that oppose the applied magnetic field B0, slightly altering the effective field of the nucleus. Now we are going to discuss chemical shift. The difference in resonance frequency due to shielding effect is called chemical shift. The formula for chemical shift is delta, which is shift. It is equals to mu of sample minus mu of reference by mu of reference into 10 to the power 6 ppm, where mu of sample is the resonance frequency of the nucleus in the sample and mu of reference is the resonance frequency of the standard reference compound, that is TMS, in proton NMR. Chemical shift help identify different chemical environments within a molecule. Applications in NMR spectroscopy. Structure elucidation. By analyzing the chemical shift, coupling constants, and signal intensity, NMR spectroscopy reveals the detailed structure of organic and inorganic molecules. And what is spin-to-spin coupling? Nuclei interact with each other through J coupling, splitting NMR signals into multiplets. The splitting pattern provides information about the number of neighboring nuclei. Now we are going to study about multiplets. Let us look into an animated video about how multiplets function in NMR spectroscopy. Since nuclear spins behave like magnets, they also influence their neighbors. One way this happens is through shared electrons in chemical bonds in the molecule. We call this J coupling. Each spin can have two states, along the magnetic field, against the magnetic field. As an example, we look into two methyl hydrogen spins chemically identical. They have four combinations. One spin down, one up. Both spins down. One spin up, one spin down. And both spins up. Each combination has a different energy level and influence in the neighboring spins, except that up-down and down-up combination have the same energy level and influence. The influence is visible as a splitting of the signal in methyl group into three. This is called multiplet. Likewise, the three methyl hydrogen spins split the methylene response into four signals. In conclusion, NMR can identify molecular structures from chemical shifts and multiplets. Now we are going to look into the applications in NMR. One of the main applications is MRI, which is magnetic resonance imaging used in medical science. MRI uses NMR principles to visualize soft tissues by mapping hydrogen atoms densities in biological tissues. Gradient fields in MRI. Electromagnetic gradient fields are applied to encode spatial information, allowing construction of detailed 3D images. So in MRI, we get 3D images of the tissues present which are damaged or which are not functional to detect what disease has been there. This is basically used to study tumors and other ruptured tissues in human body. T1 weighted and T2 weighted imaging. By tuning MRI parameters, images can be made sensitive to either T1 or T2 relaxation times, emphasizing different tissue types. Now we are going to look into the conclusion of the topic. So the fundamental properties of electromagnetism, including static magnetic field, RF, radiation, and relaxation process, are critical in NMR. Applications of NMR in both spectroscopy and imaging are vast, from molecular analysis to medical diagnostics. Future prospects of NMR. Advances in electromagnetism can lead to new applications in fields like quantum computing and advanced medical diagnostics. And these are the references which I have taken help from to make this video look good. Thank you, everyone. Hope you liked my presentation. Hope you like the topic NMR. I have taken NMR as a basic application of electromagnetics. There are many such applications which we use to work in day-to-day life. Thank you.